What is superconductivity? Superconductivity is a fascinating phenomenon observed in certain materials at extremely low temperatures. It is characterized by two key properties: zero electrical resistance and the expulsion of magnetic fields, known as the Meissner effect. This unique behavior opens up possibilities for revolutionary applications in various fields, ranging from transportation to medicine and energy. This document provides a detailed explanation of superconductivity, its key characteristics, and its potential applications. Zero resistance, the hallmark of superconductivity. In ordinary conductors, the flow of electrical current is impeded by resistance, which arises from collisions between electrons and the atoms of the material. These collisions dissipate energy in the form of heat, leading to energy loss during electrical transmission. Superconductors, however, defy this conventional behavior. Below a critical temperature, Tc, the electrical resistance of a superconductor abruptly drops to zero. This means that an electrical current can flow through a superconducting material indefinitely without any loss of energy due to resistance. The absence of resistance in superconductors has profound implications. It allows for the creation of highly efficient electrical circuits and devices, as energy is not dissipated as heat. This could revolutionize electronics, power transmission, and energy storage. Magnetic field expulsion, the Meissner effect. In addition to zero resistance, superconductors exhibit another remarkable property known as the Meissner effect. When a superconducting material is cooled below its critical temperature in the presence of a magnetic field, it actively expels the magnetic field lines from its interior. This expulsion is a fundamental characteristic of superconductivity and distinguishes it from perfect conductivity. The Meissner effect arises from the formation of superconducting currents on the surface of the material. These currents generate a magnetic field that exactly cancels the external magnetic field within the superconductor. As a result, the magnetic field lines are forced to detour around the superconductor, creating a visually striking effect. Critical temperature, the gateway to superconductivity. The transition to a superconducting state occurs below a specific temperature known as the critical temperature, Tc. This temperature is a characteristic property of each superconducting material and varies depending on its composition and structure. Above the critical temperature, the material behaves as a normal conductor, exhibiting electrical resistance and allowing magnetic fields to penetrate its interior. However, as the temperature is lowered below Tc, the material undergoes a phase transition to the superconducting state, characterized by zero resistance and the Meissner effect. The critical temperature is a crucial parameter for determining the practical applications of a superconductor. Materials with higher critical temperatures are more desirable, as they can operate at more easily achievable temperatures, reducing the cost and complexity of cooling systems. Applications of superconductivity, a glimpse into the future. Superconductivity holds immense potential for revolutionizing various fields, offering unprecedented performance and efficiency. Some of the most promising applications include magnetic levitation, maglev, trains. Superconducting magnets can be used to levitate trains above the tracks, eliminating friction and enabling extremely high speeds. Maglev trains offer a smoother, faster, and more energy-efficient mode of transportation compared to conventional trains. Magnetic resonance imaging, MRI, and nuclear magnetic resonance, NMR. Superconducting magnets are essential components of MRI and NMR machines, which are used for medical imaging and scientific research. These powerful magnets generate strong, uniform magnetic fields that enable high-resolution imaging and analysis of materials. Energy-efficient electronics. Superconducting circuits can significantly reduce energy consumption in electronic devices. The absence of resistance in superconductors allows for the creation of highly efficient switches, sensors, and other electronic components, leading to smaller, faster, and more energy-efficient devices. Superconducting quantum interference devices, SQUIDs. SQUIDs are extremely sensitive magnetometers that utilize superconducting loops to detect minute changes in magnetic fields. They have applications in various fields, including medical diagnostics, geophysical exploration, and fundamental research. Power transmission. Superconducting cables can transmit electricity with virtually no energy loss, reducing transmission losses and improving the efficiency of power grids. This could lead to significant energy savings and reduced carbon emissions. Fusion energy. Superconducting magnets are crucial for confining plasma in fusion reactors. These magnets generate strong magnetic fields that contain the hot, ionized gas, enabling nuclear fusion reactions to occur. Challenges and future directions. Despite its immense potential, the widespread adoption of superconductivity faces several challenges. One of the main challenges is the need for extremely low temperatures to achieve the superconducting state. Cooling materials to these temperatures requires specialized and expensive cryogenic systems. Another challenge is the brittleness of some superconducting materials, which makes them difficult to fabricate into wires and other useful forms. Researchers are actively working to develop new superconducting materials with higher critical temperatures and improved mechanical properties. The discovery of high-temperature superconductors, HTS, in the late 1980s, which exhibits superconductivity at temperatures above the boiling point of liquid nitrogen, has spurred renewed interest in the field. HTS materials offer the potential for more practical and cost-effective applications of superconductivity. Ongoing research efforts are focused on understanding the fundamental mechanisms of superconductivity, developing new superconducting materials, and improving the fabrication and processing techniques for superconducting devices. As these challenges are overcome, superconductivity is poised to play an increasingly important role in shaping the future of technology and energy.